Stars are the most basic building blocks of galaxies. The age, distribution, and composition of stars trace the history, dynamics, and evolution of their galaxy. Stars are responsible for the production and distribution of heavy elements, such as carbon, nitrogen, and oxygen. Like people, stars are born, they grow old, and they die. Their birthplaces are huge, cold clouds of gas and dust, known as nebulas. The most famous of these is the Orion Nebula, which is just visible with the unaided eye. These clouds start to shrink under their own gravity. As the cloud gets smaller, it breaks into clumps. Each clump eventually becomes so hot and dense that nuclear reactions begin. When the temperature reaches 10 million degrees Celsius, the clump becomes a new star. After their birth, most young stars lie at the center of a flat disk of gas and dust. Most of this material is eventually blown away by the star's radiation. Before this happens, planets may form around the central star. What really happens inside a nebula? Clouds of gas are common in our galaxy and in other galaxies like ours. These clouds are called nebulae. A typical nebula is many light years across and contains enough mass to make several thousand stars the size of our Sun. The majority of the gas in nebulae consists of molecules of hydrogen and helium, but most nebulae also contain atoms of other elements, as well as some surprisingly complex organic molecules. These heavier atoms are remnants of older stars, which have exploded in an event we call a supernova. The source of the organic molecules is still a mystery. Irregularities in the density of the gas causes a net gravitational force that pulls the gas molecules closer together. Some astronomers think that a gravitational or magnetic disturbance causes the nebula to collapse. As the gases collect, they lose potential energy, which results in an increase in temperature. As the collapse continues, the temperature increases. The collapsing cloud separates into many smaller clouds, each of which may eventually become a star. The core of the cloud collapses faster than the outer parts, and the cloud begins to rotate faster and faster to conserve angular momentum. When the core reaches a temperature of about 2000 degrees Kelvin, the molecules of hydrogen gas break apart into hydrogen atoms. Eventually the core reaches a temperature of 10,000 degrees Kelvin, and it begins to look like a star when fusion reactions begin. When it has collapsed to about 30 times the size of our Sun, it becomes a protostar. When the pressure and temperature in the core become great enough to sustain nuclear fusion, the outward pressure acts against the gravitational force. At this stage the core is about the size of our Sun. The remaining dust envelope surrounding the star heats up and glows brightly in the infrared part of the spectrum. At this point the visible light from the new star cannot penetrate the envelope. Eventually, radiation pressure from the star blows away the envelope and the new star begins its evolution. The properties and lifetime of the new star depend on the amount of gas that remains trapped. A star like our Sun has a lifetime of about 10 billion years and is just middle-aged, with another 5 billion years or so left. Some of these spinning clouds of collapsing gas and dust break up into 2 or 3 blobs that each form stars. This would explain why most of the stars in the Milky Way come in pairs or in multiples. Not all of this material ends up as part of the star, however, the remaining dust can become planets and moons, asteroids and comets, or may simply remain as dust. As millions of years pass, the core temperature of a protostar reaches a point at which nuclear fusion can begin. The star then begins the longest stage of its life, called the main sequence. Most stars in the galaxy, including our Sun, are categorized as main sequence. This is a state in which nuclear fusion in the star is stable and hydrogen is converted to helium. This process releases a lot of energy that keeps the star hot and bright, and it supplies an outward pressure against the incredible mass of material that would otherwise cause the star to collapse on itself. 90% of a star's life is spent in the main sequence phase. When you look at the night sky, you may notice that some stars shine more brightly than others. The brightness of a star is related to how much energy it puts out, as well as how close it is to Earth. Stars also vary in color, because they vary in temperature. Hotter stars appear blue or white, while cooler stars look orange or red. Astronomers use these characteristics to classify main sequence stars into categories by color and temperature: O, blue; B, blue-white; A, white; F, yellow-white; G, yellow; K, orange; and N, red, from hottest and biggest to coolest and smallest. Stars at the ends of their lives are out of the main sequence. These include supergiants, red giants, and white dwarfs. Our Sun is categorized as a G-type yellow-dwarf main sequence star. It is predicted that our Sun will remain in the main sequence phase for a few billion more years. Stars can live for billions of years, but their lives can be shorter or longer depending on their size, technically, their mass. The bigger, or more massive, the star, the shorter its life, as more massive stars burn their nuclear fuel faster. The gas and dust that swirl around a star during its formation are critical to forming planets around it. The dust contains heavy elements such as carbon and iron that form the cores of planets. Scientists think planets start off as grains of dust smaller than the width of a human hair. They emerge from the giant, donut-shaped disk of gas and dust that circles young stars. Gravity and other forces cause material within the disk to collide. If the collision is gentle enough, the material fuses, growing like rolling snowballs. Over time, dust particles combine to form pebbles, which evolve into mile-sized rocks. As these planetesimals, or planets in the making, orbit their star, they clear material from their path, leaving tracts of space empty but for fine dust. At the same time, the star gobbles up nearby gas while pushing more distant material farther away. After a few million years, the disk will have totally transformed, much of it taking the form of new worlds. When an average star like our Sun runs out of hydrogen to fuse, the star starts to collapse. But compacting a star causes it to heat up again and is able to fuse what little hydrogen remains in a shell wrapped around its core. This burning shell of hydrogen greatly expands the outer layers of the star. When this happens, the star becomes a red giant. When our Sun enters the red giant phase of its life, in about 5 billion years, it will be so big that Mercury will be completely swallowed. Our red giant Sun will still be consuming helium and cranking out carbon. When the helium is gone, the Sun will succumb to gravity again. When the core contracts, it will cause a release of energy and the Sun will become an even bigger giant, with a radius beyond Earth's orbit. After about 1 billion years as a red giant, the Sun will have ejected its outer layers until, eventually, its stellar core is exposed. This dead, in terms of nuclear fusion, but still ferociously hot stellar symbol is called the white dwarf. White dwarfs are roughly the size of Earth, despite containing the mass of a star. Pressure from fast-moving electrons keeps these stars from further collapse. The more massive the core, the denser the white dwarf that is formed. Thus, the smaller a white dwarf is in diameter, the larger it is in mass. White dwarfs fade into oblivion over many billions of years as they gradually cool down. This fate awaits only those stars with a mass up to about 1.4 times the mass of our Sun. Above that mass, electron pressure cannot support the core against further collapse. Such stars suffer a different fate. If a white dwarf forms in a binary or multiple star system, it may experience a more eventful demise as a nova. Nova is Latin for new. Novae were once thought to be new stars in the act of being born. Today, we understand that they are very old stars, white dwarfs. If a white dwarf is close enough to a companion star, its gravity may drag matter, mostly hydrogen, from the outer layers of that star onto itself, building up on its surface. When enough hydrogen has accumulated on the surface, a burst of nuclear fusion erupts, causing the white dwarf to brighten substantially and eject its remaining material. Within a few days, the glow subsides and the cycle starts again. Sometimes, particularly massive white dwarfs, those near the 1.4 solar mass limit, may accrete so much mass in this manner that they collapse and explode completely, becoming what is known as a supernova. If the collapsing stellar core at the center of a supernova contains between about 1.4 and 3 solar masses, the collapse continues until electrons and protons combine to form neutrons, producing a neutron star. Neutron stars are incredibly dense. Because it contains so much mass packed into such a small volume, the gravity at the surface of a neutron star is immense. Like white dwarfs, if a neutron star forms in a multiple star system, it can accrete gas by stripping it from nearby companions. Neutron stars also have powerful magnetic fields that can accelerate atomic particles around its magnetic poles, producing powerful beams of radiation. Those beams sweep around like massive searchlights as the star rotates. If such a beam is oriented so that it periodically points toward Earth, we observe it as regular pulses of radiation that occur whenever the magnetic pole sweeps past our line of sight. In this case, the neutron star is known as a pulsar. If the collapsed stellar core is larger than 3 solar masses, it collapses completely to form a black hole, an infinitely dense object whose gravity is so strong that nothing can escape, not even light. The dust and debris left behind by novae and supernovae, as well as by red giants puffing off their outer layers, eventually blend with the surrounding interstellar gas and dust, forming new nebulae. The products created in the ends of the lives of stars enrich galaxies with heavy elements and chemical compounds. Eventually, those materials are recycled, providing the building blocks for new generations of stars and planetary systems. After the Earth dies, some 5 billion years from now, after it's burned to a crisp or even swallowed by the sun, there will be other worlds and stars and galaxies coming into being, and they will know nothing of a place once called Earth. Carl Sagan. Want to know more about neutron stars and black holes? Check on the previous video which was posted on our channel. Thanks for watching. Like, subscribe, share the video. See you in next space adventure.